One of the best things about studying in a place like Cyprus, and I know this is a kind of a cliche in geology, but when you really study and understand what the rock record means, it really is almost like peeling back the pages of a book, in that we can read the geologic past, in that it's something much different that was ever present today. For instance, with these cliffs, we can see calcium carbonate deposition in the environment, probably not unlike what the ocean is, maybe 20-30 meters offshore, and this isn't that much different of an environment. But if we look at an area further inland, like the Troodos mountain sequence, which is made possible by the geology of the region, what's happening is as the African plate is going into the Eurasian plate, there is uplift, and this uplift allows the island of Cyprus to exist, because otherwise, as we can see in most, if not all, of the rock record, Cyprus was once a shallow to deep sea environment. And the coolest example of this is probably the Troodos Mountains, where as we walk up the Troodos Mountains, it's almost like going deeper and deeper into the earth. The Troodos Mountains is a very rare phenomenon called an ophiolite sequence, and it's a reflection of the asthenosphere on the rock record. And so as we go up the mountain, we see basalts and gabbros give way to more mafic rocks like peridotite, which is reflective of a much deeper deposition, because we don't really see peridotite or other ultramafic rocks in a normal plutonic environment. And we would only know it's really one thing to see this in a book, but to go to a place like Cyprus and to truly understand it is something completely different. And one of the important things that comes from this volcanic past is the mining opportunities that ancient people have had up to the present. The Romans valued sediment for the copper, British for asbestos, as we saw in the Troodos Mountains, and numerous other mining operations. Just now, oil and natural gas has opened up. We saw a couple of drilling rigs offshore, and it's the geology of the region that allows for these sorts of operations. And one of the areas that we thought showed the change in depositional environment, a rapid change, very well, was the gypsum outcrops. And what we thought was interesting with these gypsum outcrops was that they are a result of regressing seas, or evaporating seas. And what happens is when the seawater leaves, it leaves behind these dissolved solids. And so it's a direct representation of the change in the area. And on the other side of the coin, we saw with the sunken basilica site that seas can also transgress, and that all of these things are cyclical. The opening and closing of the basins, diverging, converging, and all of these geologic processes are constantly at work, and they have been before humankind were here, and they will be after. And as we learn about these sorts of things, and we use methods that we learn in the classroom and apply them to the real world, we can piece together the geologic past, and we can discover these kinds of things about regions, things that are of economic importance, or are dangerous, hazardous, earthquakes, landslides, things like that. And some of the things we do in the field are putting together pieces of the puzzle, so to speak. You have a really cool example here of sea erosion. So what we have here are mostly layers of calcium carbonate. Looks like alternating layers of coral and limestone here, and some other rock which is interesting. It has a feature to it, probably indicative of some sort of mineral deposit. We're not entirely sure what yet, but you can see up there this we have a marly sandstone. It's mostly sandstone. It's actually phospholiferous. It has a lot of shell material. And what happens is, since that's has less of a concentration of calcium carbonate, and it's also not in contact with the sea, what's happening is it's being undercut here, and eventually the fate of it is this whole thing is going to come collapsing down as the cliff erodes further. The weight's not going to be able to support itself. So it might be interesting to look in the next few years to see if that happens. Maybe it'll happen in our lifetimes, maybe it won't.
Also, the top layer is made out of different material than those lower layers?
Yeah, it's so that's a what looked like a marly sandstone. It seemed like it was more of a true sandstone than any of the other layers. There was a lot of limestone in it, though, obviously, a lot of shell fragments and things like that. Lots of fossils.
Is that what held it there?
Yeah,
from falling?
So that's part of it. Part of it is the composition of it. There's more sandstone in it. It's more resistant to the kind of weathering that limestone undergoes. But also, it's higher up above sea level, so it's not in constant contact with the sea. So you don't get the seawater eroding it quite as much. You mostly just have the rain and the runoff. And that would be my hypothesis there.
Okay.
There are two different environments for species to live in, and therefore two different species that lives in two different environments, just right next to each other, adjacent to each other. One of them is in the sun, right underneath the water. You would notice that there is a species that lives there are more brownish, grayish, and these kind of colors. If you move further down toward the shadow, you notice that the species that lives on these rocks here are more purplish, pinkish, and these types of color. This change, those species have their own niche. They cannot survive in the sun. Maybe they cannot compete there. Maybe they're not better at competing in a sunny environment. That's why you notice them in this environment. You don't notice you don't find the other species that lives in the sun right here, which is only like 5 feet difference in space between the two species, and yet still they still separate.
So one of the things that we did at almost every site that we went to was using the Brunton compass as well as a rangefinder. We were able to calculate the height of the outcrop that we were at above sea level, and then from there we were able to calculate the rate of uplift by dividing that from the known age of the rock. So basically what we would do is that we would stand like this here, measure the angle with the Brunton, and use the level, and then the outcrop is over here, and we would use basic trig to find the angle, multiply it by the hypotenuse, but in this case I have the adjacent here. If we were to use the tangent side, like I will here in a second, in my experiment here, if we have the adjacent side, we multiply that by the angle, and we get the opposite side, the tangent. One of the things I thought would be cool to do was there's a national monument here in Colorado Springs, and it's called Garden of the Gods National Monument. So, I thought it would be very cool to do the same thing in Colorado to show how applicable field methods are to all of these different areas around the world. 16 feet. So I thought we could calculate the rate of uplift here in Colorado. And then what I'm going to do is I'm going to use the Brunton compass to get the angle there. And once I have the angle and the distance, I can multiply the angle by tangent. And then once I have the tangent, I can multiply that by 16, and I'll get the height of the outcrop. And then I will need to add that to 6,200 feet because that is the elevation of the park. And once I have that, I will be able to do that. And so we also made a couple pretty key observations in the field. So what we see here is evidence of cross-bedding, and that would mean that we're either in a dune or a desert environment. What I thought, based off of looking in the field, was the proximity of the limestone and knowing the geology of the region. It was likely that this was probably a near-shore dune. And some of the work that I did on ArcMap confirmed that, said it was dune deposits. And most of this here is actually a geologic map of Colorado on ArcMap, and I have the coordinates plugged in. And as you can see, most of these formations are about Cretaceous in age. Some of them are older. But as we look up the as we look up the so if we look at the Larmanite orogeny, the Rocky Mountain mountain building, we find that it happened somewhere between the late Cretaceous and the Tertiary. So somewhere in the order of starting from 70 to 80 million years ago and ending somewhere between 35 and 55 million years ago. So if we take the kind of split the difference here, and we take we say that it started about 70 million years ago and ended 35 million years ago, and that's an assumption, of course. We don't know 100% for sure when the orogeny started. And then we apply the data that we obtained in the field. So if we take our angle measured with the Brunton compass times the tangent, tangent of 71 times 16 is 46.5 feet. So we need to, and then we need to consider the fact that this was probably deposited above sea level. So the observations made in the field would suggest that it was either in a desert or dune environment. Either way, it would be terrestrial due to the cross-bedding. The nearshore dune hypothesis is more likely, we think, because of the presence of the limestone outcrop that we saw, and also the fact that we know that much of the of North America was a sea at the time. So if we take 26.5 feet and then divide that by 35 million, which is the when the orogeny was active, and we're also assuming that there's no residual uplift anymore, and we're not taking into account any erosion. So there's a lot of assumptions there, but we can at least get some kind of a picture. So, and let's multiply this by 12 so we get a bit more sensible of an answer, convert it to inches. So we're going to get about 9.08 times 10 to the negative 6 inches per year. So you can see just how slow of a process this is, but it's also a very real process, one that happens, and one that over time can produce a mountain range as majestic as the Rockies, or uplift a divergent plate boundary into a mountain range, given millions and millions of years. And that is something that is very amazing to be able to do on our own, to calculate that kind of information with